because there are no, I think up until now there are no, in our scientific view, 100% crystalline on polymers, I think it's not possible. If you learn material science before, it's not possible. Unless you make a single crystal. That's 100% crystal. But for polymers, it's supposed to be semi-crystalline. Or there are, I think, some that they say that we can make it like zero crystalline and like amorphous. And then we can also categorize the elastome. This is like a rubber, okay? Like a rubber. It's like it's in between on, like it's liquid, but it's not liquid. It has some elastic property on it, right? And then we can also take as a thermoset. It has sets because they are, if I remember, I mentioned resin, right? Or epoxy. That is the common terms, I think, in the market. If you work on some, I don't know what resin you are using for. Because I believe when I was still a high schooler, I made something from resin, like making some models, and then you put something, put the reactors, for initiations, and then it's cross-link. Okay? The other term that is important is the cross-link. Okay? So cross-link. So in thermoset, cross-link is the way you connect all the links in the main chain of the polymer, and then you are getting a network. So you get a network polymers. Okay, so that's basically thermosets. Okay, let's go for some a little bit definitions, and let's see what's the difference. Okay, so thermoplastics. Okay, thermoplastics. What's the key? Okay, the important points is that if we take some process, like give temperature, increase the temperature, give heat. Okay. So you give heat and it becomes liquid. Okay. So thermoplastics. So if you see any thermoplastic, like maybe usually if you buy from the market or from the supplier, maybe you will be given like a we call it pellets, and then the pellets we put into like a processing machine. We increase the temperature, and then we can mold the polymer. Okay. So that's what thermoplastics is. Okay. So thermoplastic, we can make it a liquid, like giving energy, make a liquid, and we can mold using injection molding or extrusion. You can look up what extrusion means. It's like you put something inside, and then you push the polymers, and then maybe it comes out with some models. Okay. And then the second statement here, the thermoplastics do not crystallize easily upon cooling solid state. And then the expression Y. And there another statement here, I need you to connect this statement. Those which do crystallize invariably do not form perfect crystalline materials. So I think it's too difficult. I think. Let me explain. So if you cannot crystallize all the segments in polymers, at the same time, at the same time, let's say at the same time, then you will not have a crystalline material. So that's why I write before, there are no crystalline, 100% crystalline in polymers. We need to write, it's supposed to be semi-crystalline. Okay? So, and still, why? Okay. Anyone want to want to answer anything? So it's just saying that okay, thermoplastic, it's not crystallized, like easily crystallized when so we put the heat and we cool the polymer. And then it says it doesn't crystallize easily. Okay? And then the second one, the crystallization, okay, is not a perfect crystalline materials. Anyone has a comment on that? Why do you think the thermoplastic will not crystallize easily? Why? Do you have anything in mind?
It's not really modernamically favorable, so it can make a lot of sound for all of the chains to be
Yeah. True. But still, why is not thermodynamically stable? The clue is correct, it's not thermodynamically stable, but the clue is in terms of the polymer itself.
Because of the structure of the chains.
Yes, the chain structure. Okay. If you remember, what is the polymer in another definition? It's a macromolecule, right? It has a long chain. The molecules are big. And can we know how long the chain is? Okay. Imagine you eat noodles. That's, I think, one illustration that can describe the polymer. And we don't know. One noodle's really long, another one is small, right? So if we put like crystallize, so not everyone will crystallize the same property, same behavior. Some maybe the chain is short, maybe it's faster, but the other one maybe take times, and that's why there will be some crystalline and there will be still some amorph. Okay, got it? Okay, so why? Because noodles. Okay, let me draw here. Okay. So each length, maybe each chain maybe has different length, and that's why it's thermodynamically let's say unequal. Not stable, but unequal. I think that's maybe better. Okay. All right. And now, aside from that, remember, okay? So you need to remember, it has a long chain, and then every chain has a different length. Okay, that's different length. And when we heat and then cool, they will behave different. And that's why some will be crystallized, some will be still amorph. Okay. The crystallinity or the crystalline phase will be characterized by its melting temperature. Of course, we say about the heat before, right? And there are other characterizations which we call the glass transition temperature. Okay. So there are some region or some phases in the thermoplastics that is amorph. Okay? So let me give you another picture here. So maybe this is the crystal, and maybe this one is the amorph one. Okay, let's say the blue one here, the dark blue here is the crystalline, and this is the same, the amorphous. Okay. Okay, so the crystalline, when we melt this, and this crystalline changes its phase, that's what we call the melting. Okay, so melting is for crystalline, and for the glass transition, this is for the amorphous. Okay. So the glass transition, as you see from the terms glass, they will transform between glass and rubber. Okay. So again, still give you the sense of the rubbery state, okay, from this glass transition temperature. We will see later, okay, when we deal with the property. We will see the graph, okay, in a more clear way. But for now, let us say we know that, okay, we can know the crystallinity from the melting, and the amorph will be depends on the glass transition temperature. Okay? And this temperature also correlates with what we have as a consequence of the long chain of polymers. Okay? Long chain. I will if we finish all the slides on this part, I will give you summary. Okay? So you need to just focus on the summary if you want. So that's a classification of the polymers. Okay, this is the thermoplastics, this part. Okay, the other part we call it elastomers. We call the elastomer also can be cross-linked, but it's a rubbery polymer. It can stretch like 3, 4, or 10 times from their original shape. So that's why it's called rubber. And then they will recover their original shape when we release the stress. Okay? And that's because of low crossing density. I think pretty simple. And the thermostats, usually it's a rigid materials. Okay? They are the network materials. And then the term crosslink, because they have the network. Let me draw here. Okay. The more you have the crosslink, the more the polymers will stuck, right? Not easy to be moved. Okay, so that's why typically the thermosets will be a rigid material. I think I'm not sure in Taiwan whether you can find like a shop that maybe provide this. I think they are, right? The like resin, epoxy. Do you know? No. Because I remember when I was still in high school, back in my country, I purchased from one shop, and they give the simple epoxy. So I just put and then take a shape and wait for curing and maybe make something. Usually for you give like awards. I think like like a cup, or and it's not metals. I think most will be done with resins. Okay. And one thing really important on this crosslink, it cannot be thermally processed. So you cannot recycle. In thermoplastic, you can increase the temperature, you can give it and process, okay, and reprocess and make it into another material. Of course, there will be not really 100% because not some factors in the process. But for this cross-link, the thermoset, of course you will not be able to do that. So it's stuck in this form. Okay. Okay. Okay, that's the classifications. Okay, and then next. Okay. Next is the molar mass and degree of polymerization. So, as I mentioned, the size of polymer chain is really important. The length is really important, and because of that, the first thing we need to maybe characterize is its dimension, right? How big is it, and how many polymers or how many chains inside, right? And that's why molar mass is important. But to understand the molar mass, okay. Well, the measurement is molar mass measurement. I think you can focus just on the third statement here. So molar mass is a dimensionless quantity. It's a like your basic chemistry. So it's like relative molecular mass. Okay? And usually this is for the individual molecules is a small quantity. And of course, by multiplying with the number of the molecular weight, we can get the molar mass. Like when we say molecular weight of 100,000, we can just say that, okay, this molar mass is 100,000 grams per mole average. Okay. And for the network polymers, the molar mass is existing between the junction or the chain, the network chain. Okay. Okay. Okay, let's go for just a quick note. For homopolymer, if we take X as degree of polymerization, then the molar mass is equal to X, the degree of polymerization, multiplied with M0. M0 is the monomer, okay, the monomer. This relates to molar mass of monomers. Oh, I already have this. Okay, it's the same thing. And similarly, if you have a copolymer, then you need to add with this sum sigma. You need to add this. Okay. Add the degree and then monomers and plus. And this is the fraction, the mole fraction, and this is the repeat units or the monomer. If you confuse, the repeat unit is the monomers. Okay. Okay. Now look at this graph. One thing that is really have been in the polymers is the characterization on the distribution. So because we are talking about polymers that has a macromolecules, right? This is macromolecules, and then we know that different length, different molar mass, right? So we don't know how much molar mass. Like, okay, maybe one fraction is maybe 5, maybe 6, and how much is 5? Maybe 5, 5, 5, 5, 5, right? And it becomes a fraction. And then this, the one that's 6, the 6 molecule, it becomes 6, 6, 6, 6, 6, become another fraction, right? And we need to plus all that and then take the average number, right? Take the average number. But of course, from that point of view, we get these 3 different approaches. These 3 different approaches, different numbers, different point of view. We will go see what this is about. Okay. N is for the number average. W is for the weight, the molecular weight. Okay. So for most polymers, the intervals, the molar mass change is really small, okay, in compare with the total range of the molar mass distribution that can be assumed continuous. Okay. So we can have this typical distribution. Okay. Now let me. Okay, we get later. We will go back to this definitions later. But let me just continue for the formula first. Okay. So the number average, okay, that you see from the previous graph, okay, this is the sum of the fractions of some, let's say, substance I multiplied with the m, okay, the molar mass. So this is the molar fractions. Let me mark the important one here, and this is the molar mass. Okay. And then if we try to take these fractions and write in more general and take the ratio, we say it's n and n here, okay? And let's just write like that first. Okay, maybe if you want to write the formula first. And then later I will show you what's really the difference and how we are going to take it into example. Okay. Now we look the weight fractions. If we take a look from different angles, we can take also the weight. Okay. This is actually from the previous one. This is for the number average. Okay. If we take the weight fraction divided by m, so we will divide this one, and you see it's cancelled. So we can rewrite our number average as 1 over sum of the weight fraction over the molar mass. Okay. Now the definition of the average molar mass. The average molar mass is defined as the sum of the weight fraction multiplied with the molar mass. And this part here, we can take it from the previous equations, okay, and we can rewrite and simplify that the average molar mass is equal to the sum of the NIMR squared divided by sum NIMR. Okay. Okay, too much formula, but let me. Yeah, I think let me just take box here. Or maybe here. And also this part here. And then the definitions, the degree of polymerization. How can we compare the polymerization is based on the ratio of the number average. Okay. So we say this one is the number average and the other one is by the weight average. Two different perspectives, and we are going to see now why it's different. Okay, so this is degree of polymerizations. So if we say the degree of polymerization is 30,000, and it's asking the molecular weight of propylene. This is the structure of the propylene. I think you can imagine 3 carbons, right, and 12 the relative molecular weight, right? And then 2, 3, 6, and it's the total is 42. So molecular weight 42 multiplied with the degree of polymerization, that will be the molecular weight of propylene. Okay. I think it's very simple. Okay, let me sum up what we've done for a while above this molar mass and molecular weight. Okay, let me sum up. So molar mass, or maybe molecular weight, and distributions. Okay, remember property. Let me write here the important point. Property of polymers controlled by the chain length. Okay. And the chain, it is formed in many reactions. Okay, and then not all chains are the same length. Okay, this is pretty much summary of what we have done before. Okay, because I think some of the words may be too extensive and maybe having too many words. So we need to we need to characterize. First is the molecular weight.
Second is the molecular weight distributions. Okay, so this is the reason. Okay? This is the reason. Okay, let me give you some simplifications on the differences on
The number average and the weight average, like we did before. We see there is like MW and MN, right?
let's see what does that mean actually. Okay, maybe wait if you want to take notes. Okay.
So this is being written at the beginning. I forgot to write. So this is pretty much summarize why we need to characterize. So first is the polymer. We know the property if we can control the length. Okay? But the length itself is formed from many reactions, right? So many reactions. It can be 1,000, it can be 10,000 reactions at one time. And all chains, there will be different length. They will have different length, of course. So how do we formalize? Because they are having different length, so we need to come up with some general rule. General rule. The general rule that is the formula that we have before. We are going to find the molecular weight and the molecular weight.
Now let me give you an idea. Okay. Let me give you an idea. Okay. Let's say I have a molecules. So I have 3 parts of molecules. So molecules with 5 molecules like that. And another one is another 5. So it's another 5. And another one is 10 molecules. Okay.
Of course, from these molecules, we can know the length, right? We can know the length from the how many molecules in there. Right?
So if we going to take the average of the length, okay? So if we take average of the length, okay.
Because there is only 3, so we can just 1 multiplied by 5 plus 1 multiplied by 5 plus 1 multiplied by 10 divided by 3, the average. Okay? Just a normal average.
So 1 divide, it's supposed to be plus, so divide by 3. So it's 20 by 3. 20 divided by 3. This is about 6.66, right? Okay. So what we have done here is just the fractions. We add the fractions and multiply with the molar mass. Okay. This is what we call the number average. Okay.
The number average. So for example, if we may be having the 10 has 2, so we need to multiply by 2.
Well, you could say if this is the same thing, this is 5 and 5 is the same thing, maybe just take 2 by 5 and spend and the same number, right? Okay. So that's the number average. So number average. But of course, we can also take into another point of view. We are going to use weight. Okay? We can use weight. So if we want. So first is weight. Okay, weight. So let's say this is our weight. Okay. So if total weight is 20. Okay. We can say that the one that has one fraction of 5. Okay. One fraction of 5. 5 is 10, right? 10 by 20. It's half. Okay. And then another fractions is 10. But 10 is only 1. So it is 10 over 20, right? Or maybe let me write here that this is 5 by 2. And for 10 is 10 by 2 like that. And it's also half. Okay. So the fraction of 5, or maybe let me name this because it will be confusing. This is A, let's say this is A, this is B. Fraction of, let's say A, and this is fraction of B. Okay. So the total, if you want to take the average for the molecular weight, similarly, what we need to change, just change the N with M. Sorry, it's supposed to be like that. So this is the molecular weight. This is the fraction. What we are writing before. I forgot. Let me check. Oh, fractions is okay, and okay. Or maybe this xn is the degree. Or you can write just like fractions, like using this wi. I think maybe we can just change to w, make it the same. Okay. But here, for the molecular weight, the average molecular weight is half, right? Multiplied by 10 plus half multiplied by 5, right? So this is for A or B. So fraction multiplied by the molar mass, 10 and 5. So we have 5 plus 2.5. It's 7.5, right? It's 7.5. Okay, so you have these two different numbers. Okay, you have these two different numbers.
And as typically the polymer property, if mostly they need to be bigger on this molecular weight average.
Okay, so what we've seen here, okay, wait, this is here.
And we have a big number, right? And for the number average, this is 100, this is 199. And there's another category in the MZ, but I think I'll skip this for our course. We just focus on this two. M and M. I think we continue, right? You want to have a break? If we continue, we can have early finish class. If no, then we can have a break as is. So.
Okay, so the think yeah, this is the fractions. Okay, so we can write this if you want. You can write the mass. Okay. So example. Why I changed to W? It's correct. This is correct. Because W is the fractions. Okay, this is fractions. Okay, one example. Okay, let me try this question here. So we have a polystyrene,
and the number average for the molar mass 89,440 grams per mole. So 89,440. So neglecting contribution from N group. So N group this is the polymer. N groups you ignore, so you just focus on the repeated unit. Calculate the number average degree of polymerization.
and then assume that
The sample has molar mass dispersity.
oh, maybe before this, let me explain what is molar mass dispersity. Okay, so from here, okay,
We know the number average. We know the weight average. We can make
we call the let me write here. We call the poly dispersity index. This is equal to, or PDI. This is called PDI. This is the ratio in comparison of the weight average and the number average.
And this is also can be characterized. Which means if we know that PDI is 1, 2, 3, we know what kind of either applications or maybe what kind of polymers.
For example, we call the PDI equal 1. We call this is monodisperse. And sometimes if we have 2, and it's usually used for the step polymerizations. And if you have 3, I think not 3, maybe just make it simple. Less than 10, I mean greater than 2, then less than 10, usually for industry. Or we call the polydispersity, we can call as a heterogeneity. So if you have large PDI, then broad molecular weight. Mean distributions. Distribution. So remember, we have a curve before. So the more we have the number and the weight average, so if we take the ratio between the weight average over the number average, the more we have, the greater you can imagine. Okay, you can imagine here. Let me just explain a little bit here. If this weight increase, let's say maybe 300 maybe becomes here, it becomes wide, right? The distribution becomes wide. So if we know that the polydispersity index, we can know how the curve looks like, and we can predict how can we manufacture, what kind of manufacturing we need to do, what kind of process, because maybe we need to have like polydispersity, maybe really sharp, really precise. Then we can decide, okay, maybe we need to use what kind of polymer, what kind of polymer. And of course, in industry, why it needs large PDI? Because in industry, we need to have like mass manufacture, right? And sometimes they don't really care much, like too many, like too sharp or maybe broad, not really care much. So as long as it's get like broad and you can make some application in industry, I think that's good enough. I think we need to turn the light. Sitting there. Okay, so that's the PDI. Okay. So if we look on the question, if you want to take notes here, so please. Because the polydispersity is not only in polymer, it's also in other terms as well. But the definition is similar. So if you are talking or maybe discuss the PDI in more general unit, usually it's from 0 to 1. But in polymer, as you may see from our curve before, our weight can be different and our dispersity is ranging from 0 to 10. Or maybe more, we can have more. Okay, so back to this question here. So it's given you the information about the dispersity, which means the same PDI as before. So 1.5 is the dispersity, and calculate the weight average for the mass. But I give you this picture here to imagine or to just counting the molecular weight from this structure. So we have how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. And hydrogen, we have 3 here. And how many here? 1, 1, 1. So another 3, right? And then 3, right? 3, 3, so 6. So 6 plus 90. It's 6 or not? So 12 carbon multiplied by 8, it's 96, right? And how many hydrogen? 6, right? 6. 2 by 3, right? 2 by 3. So 3, because it's supposed to be this, right? So you have supposed to be 6, right? Right? 6, right? 6 or 8. 8, right? 8. Correct. 8. This is carbon and hydrogen. 8, 1. So it's 104. So this is the we can say the for the monomer, right? And then we have the number average is 89,440, and the monomer is 104, or we can say degree of polymerizations for the number is, why I'm writing like a factors? No, it's not factors. It's 89 or mn divided by the mo. So this is 89 divided by 104. Okay, how much? I also don't know. Let me check. 860, right? So this is degree, okay, of polymerization. For the number average, okay, for number average. This is the first question. The second question, dispersity 1.5. So dispersity is molecular average for weight divided by the number average. So the weight average is dispersity multiplied with the number average. So 1.5 multiply with 89,440. .5 multiply. Okay. This is 134,160. Okay.
Any questions? I think as long as you consistent using the formula, well, depends number average or weight average. As long as you're consistent on doing both formula, I think you should be okay. Do not mix up. Do not mix up. And at least you need some calculations, at least for your exam. But I think I will give you exam with notes. With notes. I will let you know later the notes. But I think like if you have like before, maybe in other course like using notes, I think just A4 notes. You can use both sides, and yeah. And you need to use your own pen. Do not print. Print out. But there is actually a good. Maybe that's one advice for study for learn. So when you write something, actually you try to understand what you write, and it makes you focus. And really focus is one step to understand the content. You understand or you are not understand is not really matter in the first steps. At least try to focus first. Whether you understand or not, that's different matters. First, you need to focus first. You need to focus. And when you have focus, you become mindful in your topics. You are become more aware on your understanding. Whether you maybe I understand this part, but not this one. So I need to learn this, and maybe you can search for more. I think for all learning system, for all education system, they are built with the same thing in mind. That is, the student, whoever it is, need to be focused. Well, in class, I'm the teacher, you're student, but teacher also learn. Teacher also learn. When teachers prepare the materials, the content, they also need to learn how to deliver the materials and make it better. And maybe students also give comments, give feedbacks, or maybe this can be improved using this method, blah blah blah, and that's how I think education works. Okay. Any question from this one? Okay, easy, right? Not too difficult.
Well, since the course is Introduction to Polymer,
then this will be like an introduction.
okay. Okay. Okay, that's
The first part of our introduction. Okay. So from some introduction, some classification, maybe some history a little bit, some history why we need to study, or maybe how the polymers found, and some of the process, probably a simple process, and then how to characterize. The first thing we need to do is the molecular weight. And why the molecular weight is important? If you imagine maybe acrylic acid. Acrylic acid, or any polymers you find, if you type into a chemical company, maybe from for some company like Sigma, or maybe Sigma Aldrich, or other company as well. I forgot the name. Why I forgot the name? Yeah, other company. If you look at the polymers, maybe you will discover the same polymer, but it has different molecular weight. And the difference is maybe really, really huge. For example, maybe you will find polymer, let's say polymer A is 5,000 gram per mole, the molecular weight. And the same polymer A, maybe it's 20,000. And maybe the same polymer A, maybe 100,000. Why is really important? Because this molecular weight, these differences, is also affect the property. What kind of polymers you want from this type of polymer? I mean, what applications you want? Like I said before, if you have like acrylic acid in 5,000 grams per mole, you can use it as a disperser to make the particles more uniform. Or if you make it more larger, the molecular weight, it can be a precipitate. You can precipitate. Okay? So, or if you have in the middle, that the same polymers, it can be used as for washing, like for detergent. So it has different applications. So that's why the molecular weight is really important.
Okay. Now let's come back to so this is supposed to be the part 2, which is the principle of polymerization. But before we go to the principle, let me just clarify and confirm what we have learned so far. Okay? So as a summary, I forgot the from part 1. So first we learned that polymer, maybe I'm using maybe this part. So polymers, and we know this is many, this is repeated units. Okay, and then we can also learn that polymers composed of macromolecules, right? And then it's make up a long chains, right? And then what I want to write here is a summary of what this long chains is. Okay, so consequences of long chain. First is entanglement. Okay, remember the noodle part before? So you have, like when you ate noodle, it will be entangled, right? And that's why you can snoop out the noodles and you eat one by one. Okay? And what's the implication of the entanglement? The mobility. It's not moving easily. Okay? It's not moving easily. In general, it's not. So it's reduced. So reducing chain mobility. Second,
related to the chain mobility and the entanglement also, they influenced by the temperature. Okay.
in our case, let me write as a glass transition temperature. Okay. Do you remember?
The glass transition temperature, I slightly discussed that this is related to the amorphous phase. That is emphasized that this is the temperature when it transitions from your glass state into rubber state. Okay, remember this is the name. It becomes more rubber. So the more we heat, this glass transition temperature will determine how high the temperature will be when the material is becoming rubber. Okay. So, in another way, if we increase the temperature, then the mobility can be easily stretched out. Okay, can be moved. The chain can be moved easily. And when it's cold, we cannot really move the chain, right?
So we can say so the temperature will affect the mobility when temperature is increasing. Okay, let me make a little bit smaller. Okay, number 3. What's the consequence of the long chain?
So having different size, right? And then entangle each other. And then from here, the temperature, we see that some of them that are amorphous and some of them are crystalline, right? Some of them crystalline, some of them amorphous. So we could have a property that is similar to liquids and some of them similar to solids. We call the property
As a viscoelastic. This is a combination of liquids and solids. Liquids are as in the viscose, okay, viscose, and solids as in elastic. If you look polymers, there are polymers that are really brittle, really rigid. There are polymers that can be stretched easily, like a rubber. Right? So it's really the range is really wide. The number 4. It should be number 3, but I think it's okay. Still okay. Number 4, semi-crystalline. This is,
If you look on glass transition, that's amorphous, and we could say as a conclusion that
the polymers having a semi-crystalline properties. So this is a combination of amorphous and crystalline. So the way we make our polymers,
if you want to make it more rubbery, then we need to make a lot of space that is amorphous. If you want to make rigid, then we need to make the region of the crystalline need to be larger.
So amorph is for the rubbery state, and crystalline is for the rigid state.
Yeah, this four. This is the consequences of long chains. Or consequence, you can say consequence of macromolecules. Okay. I hope when you do your assignment, you are not only just look something and then write something, but you try to know what you write, and at least you try to Google out. Right? Try to Google out. At least Google. Yeah, Google is our source. And try to understand. At least the terms. Okay, the terms like. I think some of you write the process, right? It's okay if you still don't understand, it's okay, but try to understand. Not really 100%, maybe 10, 20, it's okay. Because as long as we move on in our course, we are going to see that term that you write in your assignment.
Very frequently. Hey, by the way,
rubbery state, rigid state, or you can say rubbery and rigid.
Yeah, rubbery and rigid.
Means you want to make more tough, stable, you need to have more crystalline in the polymer. Okay. By the way, have you tried to look on the macro galeria and the model? Okay, let me show you later.
Okay, another summary. As I mentioned, because of the wide applications, if we look just on the mechanical property, which we learn later, if you look a little bit, take a glance, we will have extremely diverse applications or diverse mechanical property. Okay, what does that mean? You can have rigid, from rigid to rubbery,
from the tensile graph that is really strong, and then rubbery that is down here, and we can elongate really
extensive. Okay, and then another part aside from the mechanical property is polymer are cheap and easy to manufacture. Okay.
Easy means the synthesis process is easy. If we could have done it in a room temperature. We just need to take hits for some degree. It's not really. It's really different from metals, which we need to process the metals in maybe 3,000 degrees Celsius. Right? The polymers probably 200 degrees, 300 degrees we can process easily.
And then another advantage is it's lightweight material.
Like our bottle, plastic, if it's glass, it's really heavy. And if you maybe it get impacted, the glass will be broken. But polymers, still intact. Right?
And then, of course, manufacture also processability. This is also easy. And what's the disadvantage?
Anyone has a comment? What's the disadvantage of the polymers in general? Yes. High temperature. What else?
Thermal.
Some of them are prone to solvent.
Solvent attack. Okay.
Solvent attack. Prone to solvent attack.
Okay. What else? You realize that we want to throw our waste. We have the recycle and non-recycle. And that's the problem for the waste. So because it's cheap, easy to manufacture, then we can create this bottle in a huge number. But then it's become waste. That's why if we can use that bottles again like a thermoplastic, that's why we need to collect so we can recycle.
So, waste. So that's why we need to think of polymers that can biodegrade or biodegradability. So this is, I think, one topic that
Nowadays still good topics, still relevant. How to make a polymer that has good biodegradability. Which means biodegradability, when you put out your polymers, it will decay easily and it will not become waste. Some polymers it become waste because it won't degrade, it won't decay.
but sometimes
This biodegradable, if you want to use that polymer for a long time, maybe not. Maybe it will be decayed. Like your, if you use iPhone, your cable is biodegradable. So maybe 5 years, it will be decayed. Because I have mine that is already loose off.
okay. What else? And applications. Okay, I think as I read some of your, I haven't read all of them, but I have read some of your assignments. So some applications ranging from packaging, right? Clothes, right? Clothing, utensils, protection, right? What I want to add is we can also have for organic electronics or the super absorber, like for diaper, this is also a polymer. And for like in the semiconductor, for the thin film,
It's also application for photolithography. Some example and more. This is just I try to categorize.
the applications. Okay, and then types of polymers. If you remember, first, based on, so what polymers looks like. So first we can look on how the molecular architecture. So we have a linear, right? Linear. We have branch. We have a network. Okay. And then we have a hyper branch. That is if each path becomes 2, for example, like this. Okay. Or dendrimers. Dendrimers is similar to hyperbranch, but the difference is it will be having a segmented pattern. For example, well, if you know the meanings, the dendrimers, it is dendritic polymers. Okay. So it's like dendrit. Okay. Dendrit means it's focused on a pattern. Okay. So if we take, for example, we take first like this, and each one is having branch like that, and another branch, and it will be more defined. The figure will be more defined. The pattern will be more defined. It's like concentrated in this center. It's centered in this. So that's why it's called dendritic. You could look on what the dendritic words meaning, the meaning of the dendritic. Okay, and this is for the molecular architecture. Okay. We can also look on the order of monomers. We have a homopolymer. Let's say A, right? Same repeated unit. And we have a copolymers. This is random. A, and then B, A, B, A, B, like that. And it's randomly in order. And then alternating. And then we have a block copolymers. So it's going to be block on each side. So one block is A, another block is B. And we can have a graph. Graph is the branch. Okay. So if the main polymer is A, so we can graph B on each branch. Okay, I think I will just stop until here. There's another summary that we can rewrite later. I will stop until here. Remember that this Thursday we will have a class, so no discussion. Discussion will be next week. Okay. I'm still thinking what kind of discussion we are going to do. So please check your Moodle every week. Okay. Okay, I think that's it for today. Oh, before that, I almost forgot.